So you are welcome to the class for today. And then last week, we started by introducing ourselves to a tour of selected classifiers, where we took ourselves through the processes that often involved in the building of classification algorithms, depending on the case that we might be dealing with. So today we are going to continue with a part 2 of it, where we try to see further, and especially from where we stopped the other day. So, but before we continue for the day, let's kind of quickly took us through a quick revision of what we did last time. We started by reminding us of some of the steps that are often involved in machine learning procedures. So starting from the data exploration, we explain all these concepts. And we said that for now, we're focusing on the classification, so which is part of the supervised machine learning algorithm. As we said, there are different types of machine learning, but the common one that is often used is the supervised learning, where you have data, you can train your model using some data set. Then you test them on sets aside, and then you use other production testing or validation to make sure that it is doing fine. And we also already discussed evaluation in other editions of our settings. So we made us realize that different categories of classification algorithms. We have the one that are based on frequency table, the covariance matrix based, the similarity functions, and others. That is, others means that different their kind of algorithmic background are totally different. Like support vector machine is the statistical based method, where neural network is based on the model of the human brain or the neural system, how the neural system functions in the body. So we have so many other algorithms that the background are totally different. So they are classified as others. They are neither frequency based nor covariance nor similarity functions. So we gave several lists, and we said the list is inexhaustible. New ones are being developed on a daily basis as interest get boom in the area of machine learning and how we can benefit from it. So we did show ourselves how you train your model with example. We discussed this example where the data is divided into the training set, and then the testing set is used to check, which I compare to the idea of training is compared to the idea of induction. So in the mathematical induction, where you should try to look for a particular function that can work for all cases. See, you might not be able to see that will get you 100%, but at least it can work for all cases to acceptable level of accuracy. Once the model is well trained, then you can use the model now with new data coming in. You can use deduction to now try to predict what is going to be the output of each of these input that are coming in. So we move further to discuss that classification were basically divided into 2 major steps. We have the model construction, so where you build your model, and then we have the model usage stage. So in the building stage, when you build your model, train it, check it to make sure it's fine, then you are ready to deploy it for your client to use it for their predictive solution. It could be a company that want to predict, maybe government want to predict bankruptcy, for example. So it's good to ask people to establish companies, but then if we can know companies that are in trouble earlier enough, the government can intervene instead of allowing the company to go bankrupt. Because when a company goes bankrupt, it's not just the owner of the company that is losing. A lot of citizens, residents of that particular country will be affected. The production process will be affected, so many things. So in this case, if we can predict bankruptcy of a particular company earlier, maybe the government can decide to take over that company instead of allowing that company to bankrupt. Then appropriately, if the company is rejuvenated, management are upgraded, and things goes on well, then the owner later, if he's able to pay some amount of money, might be able to take back his company appropriately. So, because when a company go bankrupt, it's not just the owner that is losing. A lot of people that are attached to the company, their families are losing. Even the community where they are operating. Let's say maybe a medical center now, a very big medical center want to fold up. You see, fold up made a lot of things to the people that are closer to that area that benefited from it. So that's why a good bankruptcy prediction solution will be very viable for any government that want to say, okay, can we detect ahead of time a company that might likely have problems so that we can intervene? This is one of the usage that we can put our classification algorithm into. It could be also in the health informative predictions, who might be sick, and so many other things we might want to talk about. You are in civil or construction engineering sites, you want to predict a building that might come down. These things are possible because of data set that are available. So we've had data set of buildings that collapsed in the past. These data are just lying fallow somewhere. Why don't we make use of it to build models that could be able to help our engineers to predict if a particular building might suffer collapse? These are possible these days. So at the initial stage, you construct your model, then later you make use of the model to make necessary prediction. It's not that we're interested in predicting disaster, but we want to take advantage of the knowledge of machine learning to have a glimpse of what might happen possibly, and then we can take proactive steps to prevent it from happening. So that is the stage 2 of the process. So where you build it in the first stage, the second stage where you use it to test and validate before finally deploying to the final end users. And we gave examples to corroborate it. And also we described a couple of examples from one to the other. So finally, this was where we stopped last week, and this is where we're going to start. Type of learner. So we try to classify, we say generally learners or classifier are classified into 2. They call them learner because they learn from the data, so which made them become model. That's why they call it learner. So somebody that learn from the, when you provide your training data, they try to understand the data. So they come up later and then they can predict. Yeah, we are done. We can understand the data in that area now. So we can do something. So generally, they are often divided, classifiers are often divided into 2. We have the group of classifiers that are often referred to as the eager learners, and we have the other one that are called lazy learners. So what are the differences, or how do they differ from each other? See, in the eager learner case, here, it often generates a generalized model from the training data set. You see, it will build a generalized model from that particular training data. The model could be in form of rules. It could be in form of mathematical set of equations and the parameters that are accompanying it. It could actually be in terms of support vectors, as we are going to see later how support vector machine works. You see, after the training, it generates some support vector that are going to be the representative samples for the entire data. You could have like 1 million data set, but support vector from this 1 million data set that have been used for training might just be maybe 20 or 200 or thereabout. See, but there's a particular yardstick to determine what are the support vectors. So these are the characteristics of eager learner. They try to understand the data and then come out with a particular model, which we call generalized model of that particular data. So using that particular model, the class for testing data could be easily predicted. So once they build the model, then you have a model that is already built, which I said could be rules, it could be mathematical sets of mathematical equation, of course, supported with a lot of parameter or iterative parameter values that have been gotten. Now, so due to the procedural process, so the eager learners often take long time for training. Of course, since the model is already developed, the testing set or the prediction stage is often very short. It takes lesser time to predict. So once you build a model here, so you generate an hypothesis function H. So you just take this H, new data will come in from the industry, then you can use it to take your prediction. So the only time you spend more time is at the training stage, because during the training, you could train, it might not work, you have to train again. Like we already discussed, you have to train again until you check that, oh, the training process is successful. See, you train it, you validate it, you train it, you validate it. So when you are going to finally be using your model to predict, it's going to be faster because already you built a model. So examples of algorithms in this respect, they are decision tree, naive-bayes, artificial neural network, support vector machine, and a host of others that falls under this particular category. However, for the other side, we call them lazy learners. So from the word lazy, we all know the meaning of lazy. So The idea is that there's no learning that's really taking place there. What it does, it doesn't generalize. So it doesn't generalize, it doesn't generate any model for the data, but rather it will store the data somewhere. Of course, it tries to learn from the data what is the relationship between this data and the output. Why is this as someone that has these attributes is sick, but somebody that has another very close attribute is not sick? What is responsible? So it doesn't generate a finalized model for this, but rather the data are stored. So whenever you have a new sample, it will have to refer back to the training data set to check this new sample. Who are you closer to? Who is similar to the training set they have given to me? If you are similar to it, okay, I can be able to know where you belong to. So that on querying similarity between the test data, when you bring in the test data, it will try to compare the test data with the training set, which is unlike the eager learner. In eager learner, it will use the training set to build a model, and class is done with the model, with the data set. The training set is gone. Now you have a model you can take along with you that can just be used to predict. However, for the lazy learners, they don't go through that rigor of trying to build a model from the data, but rather it will store the data set. And whenever you say, okay, I have a test set, I need to test if a sample is this or that, then it will take that test sample and compare with the training set. Because the training set is already provided with the output. Okay, if you see someone with this attribute, that person is sick. If you see another person with this attribute, that person is not sick. So it will just compare the new test set with every data sample that is available in the training set to see who is similar to you. So that's why often lazy learners work on the principle of similarity. They fall under the similarity categorization of classifiers. So it will take the new test sample and try to compare with each and every training set that you have. And then we'll be able to say, okay, you are closer to this one. If you find out that you're closer to this one, and this one is sick, then to say that, okay, that means this new test set is sick. So this is the idea of lazy learner, and we're going to look at examples. So lazy learners are also referred to as instance-based learner. Instance-based learning. See, instance-based learner, because the learning is just done based on instance by instance. So as when you bring in your test case, we try to go back to the training set and try to see who are you similar to. So most of them, they work on the principle of show me your friend, I'll tell you the kind of person you are. As we are going to see one of the popular examples now, shortly, inshallah. So in terms of comparative analysis between the two of them, so compare it with the eager learners, lazy learners have lesser training time because indeed, there's really no training taking place. You just need to take the training set and put it somewhere. You see, put it somewhere, get ready to bring in test sets. However, the testing site, the prediction time is going to be really huge. And this is why one of the disadvantages of lazy learner. And just like we all know, laziness is not something that is encouraged. So to give the name lazy learner, so indicates they don't do the rigorous work of trying to build a model, which will make the prediction faster, but they just get the data, put it somewhere. Okay, give me your test set. I will tell you the answer. And sometimes they work fantastically well, depending on the problem. And then we're going to give some couple of guidance, like they often work when the data set is not big. When you have very few samples, not huge sample. When you have big data, imagine having to compare every test set, every test sample you have to compare with all the training samples. What if you have millions or billions of training sets? In that case, the comparative stuff is going to be really huge, as we are going to discuss later on. So example of classifier in this category include the popular Knearest neighbor and also the case-based reasoning. So they are based on the principle of, okay, keep the training set somewhere, and then whenever we have a test set, then we are going to compare it. So that is about the two type of learner that I often come across. Either you lazy learner or you belong to the eager learner. But majority are on the side of the eager learner. while the lazy on the other side, though few in number. Now we're going to take the first example of classifier to be discussed, which is going to be K-nearest neighbor. KNN means K-nearest neighbor. So as we just discussed, it's one of the often referred to as lazy learner algorithms. So it doesn't store, it doesn't really produce any generalized model from the data, but rather it stores the training set you provided. And then whenever there's need for prediction, it will compare the new inputs with what you have in the training set to see where do you fall to. Now, so we're going to look at it briefly. What is K-nearest neighbor? How does it work? Then advice on how do we choose the value of K, which is one of the very important hyperparameter when it comes to K-nearest neighbor. And then we have considered a couple of examples. Then we are going to discuss the advantages and the disadvantages of it. Now, in principle, K-nearest neighbor is one of the simplest supervised machine learning algorithms that are mostly used. So very simple. And like we said in machine learning, it's always advised that keep it simple. Keep it simple. The idea is that you start your modeling, you want to predict, start from the simple algorithm. It is when the simple algorithm fails, then you go into the other one that are more complicated. See, this is the idea. But often you start with simple one. Don't just go to the complicated one, because sometimes complicated algorithm might miss the hidden relationship within your data because it's thinking too high. Just like we know, sometimes what they used to say in one adage, sometimes the kids might not be able to do something. You need an elder to do it. But sometimes also there are something that elders cannot do. You need kids to do it. If something falls inside a small jar, so something falls inside a small jar, you want to pick it out of that jar. As an elderly man, you cannot put your hand inside it. It will not enter. And if you force your hands inside it, your hand will not be able to come out. In that case, you need a kid to come and use his very tiny hand to put it inside and bring that in for you. The same thing works in machine learning. See? So there are tasks that, you will need very powerful algorithms to solve it, but you don't really know because you let the data speak. As I used to say, always let the data speak. So you don't know, maybe something like the jar that you need a kid's hand to be able to solve the problem. So if you go ahead to use your hand by force, you might have yourself to blame. So something similar in this respect. So either lazy learner or eager learner, we need each and every one of them whenever you have a new problem. So if anybody brings you problem to solve, the first thing is you start from the simple one, which is, for example, K-nearest neighbor, very popular. So it classifies data based on how its neighbors are classified. This is the idea of neighbor. It works on the principle that I often called, show me your friend, I will tell you the kind of person you are. This is what we are saying here. I think it's a very common aphorism worldwide or in most places. Show me your friend. I think you have to be very careful of the kind of friendship you keep. So if your house is located in an environment that they sample like 3 people to your left, 3 people to your right, they are all good person, then we can conclude with very high level of accuracy that, you are a good person. And if it is otherwise, you also understand the implication of that. This is the simple summary of how K-nearest neighbor works. So K-nearest neighbor stores all the available cases, that is the sample, the training set you have provided. You see, the training set you have provided, it stores it, and then classify new case based on the similarity measure. So like I was saying, it stores all the available cases. By the case, you mean the training sets, or the training set, the samples in the training set, and then it classifies the new cases that are coming based on the similarity measure. It tries to say, okay, how close are you to those training sets that I have? Because I already know the output of those training sets. That is why it is a supervised learning. So the one that came in, the test is what I don't know the output. So I will know your own output by comparing you with other training set samples that I know their output. So I compare you with like all of them. So which ones are closer to you? Maybe I look at the weight, I look at the age. So I try to compare your age and weight and see, like, who are you closer to? Some people will be closer to you in terms of age, in terms of weight. Then we try to select how many people are closer to you. This is where the idea of K comes in. K nearest neighbor. So we're going to select how many K you want to use. And that's why K is the main hyperparameter for K nearest neighbor algorithm. The hyperparameter, they are the parameter that will influence the performance of your model still significantly when you change them. See? So, for example, the K could be 1. It is the number of nearest neighbor that you want to you want to be used in deciding, because there's going to be a majority voting process. You see, I have someone here, this is a new sample given to me. I need to classify this new sample. And I have like several other samples. So I'm going to see who is closer to you. So usually the first one is K is equal to 1. So in that case, you want to detect where I belong by just checking one of my neighbor. See, sometimes it works, but then it's not really the best. But then let the data speak. We have seen data say that you try K is equal to 3, it doesn't work. Only K is equal to 1 will work for you. There are cases like that. Then you have to go by it because the data will speak for you. Now, so once you select the K, usually it could be 1, it could be 3, it could be 5, and on, depending on the case that is being treated. Now, so we say we can assign K value ranging from 1, 2, 3, 4, 5. We are going to discuss also further as we move on. So K is assigned as a class of single nearest neighbor, if that's what we want to work on. So we let the data speak. Later, data will tell us how many K you want to use. You try 1, you try 2, you try 3, and then the case may be. Principle, briefly, this is what we're talking about. So these are the training set given to us. You have here, you have here, you have here, you have here. So we want to see, this is the new sample you don't know. This one you don't know how it works. We come back to it. How do we identify it? Now, so once you have after K, another important thing to take note of is the similarity measures. You see, it's the similarity measure. The hyperparameter number 1, the first hyperparameter for K nearest neighbor is the K, the value of K. Because as I said, we are going to check it out. I have a neighbor here, I have a neighbor here, you have a neighbor here. This is the guy I want to check. I find the distance between this guy and this guy, distance between this guy and this guy, distance between this one and this one, distance between this one and this one, and distance between this one and this one. So I find it, you can see actually that this one will be closer. So I now decide, okay, how many K nearest neighbor do I want? Only 1. If it's only 1, if it is only 1 nearest neighbor I want to use, if it's only 1 nearest neighbor I want to use, then I will just assume that this sample, any class that this sample belongs to, is where my new sample also is going to belong to. That is using K equal to 1. I might have my K to be equal to 2. But then if you have 2 class problem, you want to predict if something is yes or no, then you cannot use 2, because in that case, there could be a problem with your voting. There could be a tie, because maybe this belongs to class 1 and this one belongs to class 2. So, and these 2 are the closest to it. If I want to use 2 nearest neighbor. So in that case, there's going to be a confusion. Where do I put it to? Is it class 2 or class 1? That's why if you are dealing with binary classifier or binary classification problem, you are advised to use odd numbers value for your K, so that when you are going to vote into the 2 classes, yes or no, you can be able to have majority voting appropriately. Now, apart from the K, another very important measure is the similarity measure, because when you want to I was talking about having different samples, and then you want to find the distance between a sample and the other training set. These are the training set. You know the classes of these samples. That's why we said when you give training set to lazy learners, like for example, like K nearest neighbor, they store it in the system. Now, when new samples are coming, this is the new sample that is just arriving. So we want to find out which class does it belong. So since this one are labeled already, positive, negative, you just need to do comparison. But then to do the comparison, you need to find the distance between this new one and every member. How do you find the distance between them? That's why we call it similarity measures. You want to find the similarity between them. How similar are you? How is this new sample similar to this sample? Since we know the class that each of these belongs to, if we know which one are more similar to this guy, we can be able to say that, oh, you are likely going to belong to the class of your friend. This is why I said, show me your friend, I show you the kind of person you are. Now, we said that it should be noted that there are common distance measures that are often used. So we have the Euclidean distance, the Manhattan distance, we have the Minkowski distance, and also there are a couple of other ones. So these are very common ones. These are valid for continuous variables. For continuous variable. However, when you have categorical variable, because there are variables that don't have values. For value that has values, for variable that has value, we call them continuous variable, which means the values are like numbers, 20, 20.5. When you have categorical value variables, like you want to know about the gender, see, gender, male or female. So in this kind of case, then you cannot use this kind of distance measure. You go for the distance measure that can work for categorical variable. And one popular one is the one we call the Hamming distance. The Hamming distance is calculated thus. This is the formula for Euclidean distance. This is for Manhattan distance. This is for Minkowski distance. They are just formula. People came up with it. Mathematician knows more about this one. They came up with formulas that, okay, these are, and if you use these distances, you'll be surprised that depending on your data set, sometimes Euclidean distance might work for you. Sometimes Manhattan might work for you. Sometimes Minkowski might work for you. So this is why, in addition to the K, I've identified the hyperparameter to search for. One is K, number one is K. The K, the number of nearest neighbor. You have to search for it. Is it one that worked for me? Is it 2? Is it 3? Is it 4? You keep searching until the performance goes up and then it comes down. The one that gives you the maximum, that's where you're going to start. You are going to stop. So you run it with 1, you record your results in your Excel, it goes up and then it comes down. Then I'm going to see it here. Maybe my best value could be 5. Then I'm going to use that 5 as the hyperparameter value K that I'll be dealing with. After that, you move to which of the distance measure will work for me. Is it Euclidean distance? Is it Manhattan? No one can really tell you. So you need to check using your data, the trainer set, by checking appropriately and then validating it to be able to know which one is going to work for you. Based on the principle of let the data speak. Now, the next is the distance measure. So you have to check for Euclideans, check for Manhattan, check for Minkowski. And for the Hamming distance, which is when you have categorical variables, this is how it works. The distance between male and male is going to be 0. Distance between female and female is going to be 0, but male, female is going to be 1. This is how Hamming distance works. It's a simple formula. If X is equal to Y, if the value of this variable is the same as the value of this, maybe this is sample 1, this is sample 2, it's okay. The distance between them is 0. But if they are different, the distance is going to be 1. That is when you have categorical variable. So Ham with these two measures, the distance measure, then you are ready to implement your Knearest neighbor algorithm. So these are the two very important hyperparameters that often affect the performance. Now, let's look at how KNN works. The first step is you calculate the distance. That is, you are given this sample. This is the new sample you don't know. New example to classify. You want to predict. All these samples are known. These are diabetes patients, for example. You can see in red. Why these people are non-diabetes patients. Now, a new patient or a new person, I want to check the status, if it's diabetes or not. So you pick it, You calculate the distance between this new sample and all the other samples. You know, these are the training sets. These are training sets. Training set. And it's already stored. All these samples are stored. That's the first step. Then you calculate the distance between these and each and every one of the training samples. Once, then you find the closest neighbors. This is where you have to try how many K. You select your K, set your K is 1. Okay, find the closest neighbor 1. The one closest neighbor, you can see here. If I'm using 1, this is going to be the closest neighbor here. So I will just conclude that the new sample is diabetes because the only one closest neighbor is this. And show me your friend, somebody that is so close to you, they are saying it's likely you are also in the same level. Or I want to predict somebody is good. Or I want to predict somebody is going to pass an exam. And I want to use Knearest neighbor. If you always move with somebody who is really, really very brilliant, most likely you're going to pass the exam because you have the opportunity to discuss with him, solve tutorial together. So this thing works. It's not random, actually. However, if you are the one that always stay with the one who are not serious, who doesn't want to study, most likely the person is going to fail. So this is the idea of Knearest neighbor. So if you surround yourself with people that are good, most likely you'll be affected. And I think even our religious subscription do teach us this, that we have to be careful about the kind of friendship we keep. So this is a kind of a big summary about Knearest neighbor. So I've chosen my K to be 1. So I'm just going to classify this new sample as belonging to diabetes patient, the red class. And I'm going to stop. That is it. See, since K is equal to 1 and I choose 1 and the only one is this, so I can easily take it. But if I say K is equal to 3, for example, I want to select the first 3 that are closest to me. In that case, I might have to need vote. Step 3 becomes compulsory. See, step 3 becomes compulsory. Vote for the labels. See, because what is going to happen is this. Let's look at this example. This is class A, this is class B. You calculate the distance. This is calculated. Now I want my K to be 3. So you can see I selected the 3 closest samples to this new one. We don't know where this one belongs. So this is closer, this is closer, this one is closer. So you can see you selected these 3. We calculate the distance. How do I know who is? Now, please let me clarify this. We are looking at the diagram to make it easy for us. But when you want to do it, you have to calculate the distance using the distance measure we discussed. You will know who is closer, who is not closer by that. So we select these 3. Now say K is equal to 3. Now we are going to vote now because now we have K more than 1. So we're going to vote. The green class, which is class B, has how many votes now? 2 votes. The red class is having 1 vote because it's only 1 coming from the red. So 2 against 1. It means for this, when I use 3 nearest neighbor, now I'm going to classify this unknown label to be class B. Class B. You can see now when we use only 1 class, it was classified as the red class. But when I increase it to 3, because it's going to be an error. Only one person is close to me, and that card happens to be bad. It doesn't mean someone is bad. Maybe you have other 50 friends. So that's why some people have the opinion that it's good to check more number of Ks. Don't just use 1 K is equal to 1 and you stop. No. Use K is equal to 1, K is equal to 3, K is equal to 5. If you are working with binary classification, yes or no, then you can be able to see which one is performing better for you. So once you detected that, then you build your final model using that. This is how Knearest neighbor works. Now, in algorithmic format, this is the summary of the algorithm. So you start by choosing K, the value of K, very important. So for a given new instance, the new instance you have, the new sample you want to predict or classify, you find the K closest training point with respect to a distance measure that we discussed. So you don't classify this unknown sample is going to be classified into the majority vote among the K points, which I just explained in the previous slide. So the one that are majority, if class A, class B, 5 people from class B are closer to me. 3 people from class A are closer to me. That is 5 against 3. So I'll be classified to belongs to class B. So this is how it works. Next. Now, how do we choose the value of K? Choosing the right K value is very important. So it's in a process called parameter tuning. I once uploaded a video in our channel on this, how to tune your parameter, and more will come on that under that one later, inshallah. So parameter tuning is where you try to check which parameter is going to work for you. We've identified 2 hyperparameters for this algorithm, K-nearest neighbor, K, the K value, and also the distance measure. But K value is really the number one we have to care more about. So in a process called parameter tuning, which is what I just explained, you set it to be 1, you set it to be 2, keep checking different one until you get the one that is working for you. Now, so we said this pair is not the number of K-nearest neighbor. You have to choose it, of course, at the beginning where you are trying to build your model. So it is the kind of the main controlling variable for the prediction model you are trying to develop. And if you are able to choose the appropriate K, then it might be better for you. You might be able to get good results. A lot of suggestions were given by people. For example, people believe that a large K value is more precise as it reduces the overall noise, but there is no guarantee. This is why some people say the best value of K is between this and this. But my own position has always been, since you have training set, let the data speak. So putting your data into the system, running using K is equal to 1. You have an Excel file, plot it there, plot your results. I got this value, this is the accuracy you are getting from 0 to 100. Change it to 3. If it is 2 class problem, 5, 7, 9, 11, 13, 15, keep going. And I have my automated plotting. It goes up. As I'm changing, you can see the accuracy was going up. Oh, interesting. Suddenly it goes up and then it started going down. At that point where it started coming down, we noted it down. We say, okay, it means it seems the best value, the optimal value of K is 11. To me, this is the best way to know the value of K. Some people will suggest for you to try to study your data set. If you spend 1 year studying your data set, you still cannot guarantee which K is going to work for you. So rather than wasting time on that, I usually go for let the data speak, do parameter tuning, try to check, let the data tells the system the kind of K value that is going to work for it. And this is the best sure way for you to get the best result that is possible. Of course, there are a couple of advices, like I just mentioned, on how to choose K. It's just tips. Choose odd number of K value for 2 class problem. This is normal. This is a common sense, because if you have 2 class problem, your K cannot be 2. Because if K is 2, class 1 has 1 value, class 2 also has 1 value. How are you going to vote? That's going to be 1 against 1. So there'll be confusion. So that's why you can use 1. It means one of the classes we have the 1, the other one doesn't have any value, which means it's okay, we can vote. That is 1 against 0. I can choose 3, one is going to have 2 against 1. I can use 5, one is going to have maybe 3 against 1 or 4 against 1, but never choose even number when you are dealing with 2 class problem. This is a very valid point that you have to take note of. Now, we also that K must not be a multiple of number of classes. That is, K should not be multiple of number of classes, depending on the problem you are solving, because that could also lead to the same problem. For example, if I have 3 classes, that's the rule of thumb for saying that 2 class problem, because it's very common, we treated it generally, specifically, that don't give even value for the number of K. This tip is generalizing the idea that the general idea is that the number of, don't choose K that is a multiple of number of classes. Because if I have 3 classes, I have class 1, class 2, and then class 3. In that case, if your K, this is 3 classes, if K is equal to 3, that's going to be a problem here. Because each of them can have 1 votes. Then our problem voting. That's why we say that the number of K must not be multiple of number of classes. I think this is simple mathematics, also simple arithmetic. Hope we get that. We said the main drawback of k-nearest neighbor is the complexity in searching the nearest neighbor for each sample. This is the main problem with k-nearest neighbor. Of course, it was lazy. It doesn't do any training to generate a kind of universal model to be used. It stores the data. So every time you have a new sample, you have to compare the data with each and every sample and then arrange them to see which one is closest, which one are the closest one to this value after computing the distance measure. So in this sense, it's going to take a lot of time, especially if your data is huge. And that is why k-nearest neighbor is recommended when your data set is not that very big. So cross validation also is often recommended as a way to retrospectively determine a good value of k by using an independent data set to validate the k value. So you divide your data, use it to check on the training set. You have the validation set aside that can check if that particular k value you have chosen is working. However, historically, the optimal k for most data sets has been between 3 to 10. This is people talking from experience, which produce better result than one nearest neighbor. But however, like I said, my own personal advice, in addition to all these, is always let the data speak. Let the data speak, because data sets are coming out these days that are breaking the rule that people know about every algorithm. Because things are changing. The way we do things are different now. The kind of food we eat are different. So people develop model to predict somebody is going to be diabetes a few years ago are coming to be surprised now that diabetes is breaking boundaries. Very young kids are having it, which was not the case before. Or even if they are the case, there are not many. So that's why new data set coming in might not behave like what people know. That's why I always tell people, yeah, advices could be given. The best value of k is this. The best value of method is this. But let the data always speak for you. So once the data speak out, it will be able to tell you how should I go about it and what's the best way for me to get the value of k, which is the best value of k that will work for me and get me the best result. Because the aim and objective of developing model is to get prediction that are very accurate. You don't want to predict with very bad kind of reliability. So which one will work for you is not, these are just tips, but the best way and my own recommendation is to go for let the data speak. And we've demonstrated it before, and we're also going to demonstrate it before we finish a k-nearest neighbor in Weka. How do you develop k-nearest neighbor? Why we are going to use a live data set to also demonstrate. Now, so this is just an example for you, and I'll give us as a kind of take home to go and work it out. You can work it out yourself. Use your calculator. Try it out on this is algorithm, how it works. When you just click it on the software, it's not magic. How does it work? So we want you also to try it out personally. Now let's look at this example before we call it a day. Consider a data set having two variables. We have a math grade and we have CS grade. So on each point is classified as either pass or fail. You are see there. This is the training set. So this is math grade. This is CS fail. This one got math 3 fail. Pass. So now you are being given this data. So this data set is your training set. This is training set. You are going to store it. Training set. You are going to store it in the system. Now I have a new grade now, 6 and 8. Someone scored 6 and 8. Now your system needs to predict if that 6, the student got 6 in math and 8 in CS, is it going to pass or fail? This is what you want to predict. Now, how do you solve that? So you have to select one, the number of k. How many k do I want? The first thing is try to calculate the distance between this sample. This is the new sample now. We don't know it, new. What is the distance between this sample and each and every sample? Distance between this and this. Distance, what are the distance between this and this? Once you know the distance, then you can select how many k am I going to select. So when you select the number of k, you now say, okay, what are the nearest k to this particular example? See? Now, this is the example. This is the solution to the example. To make it clearer, you can solve that on your own. We are using Euclidean distance, by the way. It will be interesting for someone to use Manhattan distance and see how it works and the difference you get. Sometimes Manhattan might push you to another class, actually, depending on the problem you're solving. So now, the distance between, using Euclidean distance, the distance between this sample and the first sample is 5. This one is 1. This is distance. So this is how far they are. From this, you can see that the closest, we want to use K. Let's say our K. Now we are solving it. Our K is equal to 3. Let's say K is equal to 3. In this case now, we're going to have 1, 1, 2. This, because we're supposed to arrange it in order, but then we can easily figure it out. If you have huge data, you arrange them in order. So in ascending order, the distance as they grow, we're going to have 1, 1, 2, 3 point something, then 5.3. So I select the first 3 because I'm using the Nearest neighbor, the first 3 samples that are closest to this new sample. We don't know where it belongs. So this one, this is 1, it's a pass. This one is a pass. 2 also is a pass. So it means all the 3 guys that are closest to this new student, they all pass. So we're going to say that the result is pass. This guy is passing according to using 3 Nearest neighbor. Even if I decide to use K to be 1, you can see the first one is 1. So it could be any of these 2, it's still going to be 1. But sometimes we might not have it like that every day. So let's say you have a problem to solve 3 and 4, 3 and 2. You see, you need to decide now, 3 and 2. So you have to calculate the distance between this value and this one, this one, this one, then rank them in their order of size. We want the smallest. Smallest means the closest. So what is the closest value to this thing? 3 of them, select 3 for me. Then based on the 3, we can take a vote where they're going to belong. So this is how Knearest neighbor algorithm works. And that is an example for us. And this is an activity for us to try to check it out within ourselves. And from there, we're going to take it next week to see how do we implement it. We try to implement an example in Wika, inshallah, and see how it works. And then how can you improve your result if it really doesn't work? And which order can you actually do the parameter tuning, which will assist you to select the best value of K. So we can see here the activity says solve it using Knearest neighbor. So you can decide to use Euclidean distance. You can use Manhattan distance. It's just a matter of little differences. So like I was saying, so if you can see here the 50 and then the 170, you try to compare, you find the distance between this and each and every one of them. See? So this is the class. You want to see somebody has this weight and this height. They say this one is underweight, this one is normal, this one is underweight. So you want to see, is this person going to be underweight or normal? So solve it using Knearest neighbor, choose different value of K, try for K is equal to 1, K is equal to 3, K is equal to 5. Are you going to get the same answer? Is one K working for you and the other one is getting less bad result? So when you try it out, that will give hopefully a better understanding of the system. So this is why we're going to call it a day, inshallah, for the day, so that next week, inshallah, we will continue to discuss, we've completed it, and then we demonstrate it in Wika environment, how you use it to solve real life problem. Bismillah. Thank you.